Welcome back to Stutor's, and this is the third lecture of complex number. So let's move on to the topic. So today the topic of discussion is argument of complex number, polar representation, Euler's form, de Moivre's theorem, and the most important cube root of unity. So the first topic is argument of a complex number. Let's read the statement first. If point P xy represents a complex number z, then the angle line OP makes with the real axis taking the anti-clockwise direction is known as the argument amplitude of z denoted by argument of z. Leave the statement. Let's understand that. So in an organ plane, I plot a complex number z in the first quadrant. So this is my z. Now as I said, mod z is the distance from origin. So this is mod z. Now what does argument define as? It is the angle made by this particular complex number to the origin by making an angle with the positive x-axis, that means the positive real axis, in the anti-clockwise direction. Do you understand that? This is my complex number z. Argument of z is the angle made by z with the positive real axis in the anti-clockwise direction, and not in the clockwise, it's in the anti-clockwise direction. Please do remember that. Now, if the complex number was in the second quadrant, if the complex number be in the second quadrant, then the argument of the complex number will be the angle made by z with the positive real axis in the anti-clockwise direction. So this is my theta. It's in the anti-clockwise direction, right? So if it was in the third quadrant, it would be somewhere like this. The angle made with the positive real axis in the anti-clockwise direction. Yeah. So this is my argument of the complex number. And if it was in the fourth quadrant, then it will be somewhere here. Again, it's angle made by the positive real axis in the anti-clockwise direction. So this is what argument is as defined. And argument lies between 0 to 2 pi. It starts from here and ends at here at 2 pi with one complete rotation. After every complete rotation, it repeats also. And from this diagram, we can conclude that tan theta is equal to imaginary of z divided by real z. It does not seem like a tough thing. See, as I discussed, this is my complex number, and this is my imaginary, this is my real, right? Let it be some x comma iy. So this distance is x, this distance is y. So what is tan theta? This is theta. Simple trigonometry. Tan theta is equal to y by x. So y is the imaginary part of imaginary part of z, and x is the real part of z. Hope it is clear for you. Let's move on. Now, what is principal argument? We have discussed argument. Principal argument is almost the same with a slight difference. Principal argument makes an angle with a positive x-axis in the least possible way. If it was in the first quadrant, if my z was in the first quadrant, this is my least possible way also. Rather than moving like this, I can move like this only, with the least possible way. With the positive real axis, I made an anti-clockwise direction in the least possible way. So, if your complex number is in the first quadrant, then the argument and the principal argument are the same. If it was in the second quadrant also, the argument and principal argument remains the same. With the positive real axis, if you make an anti-clockwise direction an argument, that will be only your principal argument also. But if it was in the third quadrant, if your z was in the third quadrant, rather than moving like this, you can, rather than moving like this, I'll make a dotted line. you can move in the clockwise direction to make the least possible way. So if your complex number was in the third quadrant, then the argument will be in the anti-clockwise direction with the positive real axis, but the principal argument will be in the clockwise direction with the positive real axis. I'll say how to remember it. It is simple. And if it was in the fourth quadrant, rather than moving like this, making such a turn with the positive real axis in anti-clockwise direction, you can directly come here by making a clockwise direction, right? So, argument of a complex number depends on the quadrant in which lies. In place of taking long route for taking an argument of a complex number lying in the third or fourth quadrant, we can also go with the clockwise direction. That's what I have discussed now. If the clockwise angle is used, then it will be the negative and also the negative that we will discuss now. Now, I'll just currently off this. Yeah. Now, what are the method of just learning this? We'll learn it step by step. Now, step 1, for an argument of a complex number, just find what is tan mod y by x. See, suppose your z was, let's say, 1 plus I. Your x is 1 and y is 1. So, theta is equal to tan inverse. Sorry. Theta is equal to tan inverse y mod y by x. Then what is your theta? Tan inverse modulus of 1 by 1. That is 45 degree. This is your first step. Even if it was negative, like it was minus 1 plus I, theta is equal to tan inverse, it's modulus of minus 1 by 1. Again it is pi by 4 only. So take the mode value of x and y and find the theta value. This is your first step. So the first step is find theta is equal to tan inverse mod y by x. Your first step. Now, your second step is to find the quadrant in which it lies. Let's take these two examples. Here, before moving to specifying the quadrant, I need to say the polar form of that also. So let's have a discussion with the polar form and then come back to this. Simple. Polar form is simple. Like, if I have a complex number z over here, I'll draw a line. This is my mode z. Okay. So this is my imaginary part and this is my real part. So let's say some x, let's say some y, and let's say this is some r, and this is the theta angle, right? So what is y? I think you know the basic trigonometry. Y is the opposite side of the angle theta. So what is sin theta? It is y by r. Then y is equal to r sin theta, right? Y is equal to r sin theta. Similarly, what is x? X is the adjacent side. You know what is cos theta? Cos theta is adjacent side by hypotenuse. So it is simply x by r. So what is x? R cos theta. So this is the polar form of a complex number. What is the polar form? If z is equal to x plus iy, then the polar form is x is r cos theta plus y is r sin theta, I into r sin theta. This becomes r, if I take common, cos theta plus I sin theta. Is that clear? Now, what is r? R is the mode z value, right? It is the distance to the origin. That means root of x square plus y square. Now let's move on to this example. What is the r value of here in the first case? X is 1, y is 1. Then it's root of 1 square plus 1 square. What is r in the second case? It's again root of 1 square plus 1 square. So r, you understand, it's a distance from the origin. Okay. Now, if I see this in the polar form, this is my cos theta term, this is my sin theta term, and here also this is my cos theta term, and this is my sin theta term, right? So, the second step in finding the argument is, we will discuss this once more. I just want you to know what is the polar form. That's all. We will be discussing, we will be coming back to that. Don't worry. So the first term implies the cos theta term and the second term implies the sin theta term. So in the first case, z is equal to, this is the step 2. Z is equal to 1 plus I. Cos theta is positive. Sin theta is positive. So which is the quadrant? We know this. All silver tea cups. All positive, sin positive, tan positive, cos positive. Right? So, since cos and sin is positive, it should lie in the first quadrant. So, you have specified what is the angle theta. Secondly, you have specified which quadrant does it lies. Now, the third step. And for the second case, let's take the second case also. It's minus 1 plus I. So, it is minus 1 plus I means cos theta is negative but sin theta is positive. So, it should lie in the second quadrant, right? Now, the third step is very important. Third step is a particular Cartesian. You have to remember it. If it was in the first quadrant, then theta will be its argument. If it was in the second quadrant, it will be pi minus theta. If it was in the third quadrant, it will be pi plus theta. And if it was in the fourth quadrant, it will be 2 pi minus theta. This is for argument of a complex number. So the first step is to find what is theta. Theta is equal to tan inverse modulus of y by x. Second step is to find which quadrant does it lies. And third step is to remember this. You can just remember this like this. If it was in the first quadrant, theta, don't worry about that. If it was in the second quadrant, let's say somewhere over here, then I can say that it moves pi minus theta. Read after me. It moves till pi minus theta. If it was in the third quadrant, it moves till pi plus theta. Third quadrant. If it was in the fourth quadrant, it moves till 2 pi minus theta. Right? So theta, pi minus theta, pi plus theta, and 2 pi minus theta. Hope you get it. So this is what the steps for argument of a complex number. Now for principal argument, there is no difference in the first and second step. First step, you have to find out the tan inverse theta is equal to tan inverse modulus of y by x. Second step is to specify the quadrant, and third step there is a slight difference. Now this is a recorded session, so pause the video, write these notes. These are very important. So what is the difference in the principal argument of third? While discussing the principal argument, I said that there is no difference if the z lies in the first or second quadrant. The argument and the principal argument are same. But if it was in the third quadrant or fourth quadrant, instead of moving in the anti-clockwise direction, I can move in the clockwise direction. Right? That's what I told. So, if it was in somewhere here, if my z was in the third quadrant, read after me. I'll move in the clockwise direction, and the clockwise, if I take anti-clockwise as positive, then the clockwise will be negative, right? So, if my z was here, I'll move minus pi plus theta, right? Minus pi plus theta. So, in this minus pi plus theta. And if it was in the fourth quadrant, do I need to move all around the anti-clockwise direction? No, not required. I can just move in the minus theta direction, in the clockwise direction. So this is minus theta. So this is for principal argument. Theta, pi minus theta remains the same for argument and principal argument. If it was in the third quadrant, for argument it is pi plus theta. And for fourth quadrant it is 2 pi minus theta. Now for principal argument, first and second remains the same. Third and fourth differs. How? Read after me. It moves in the clockwise direction, that is minus pi plus theta. Right? If it was here, it moves in minus pi, comes back to theta. So minus pi plus theta. And if it was in the fourth quadrant, just move minus theta. Hope this is clear. This is the concept of argument and principal argument. Very important. Must learn. Okay, let's move on. Polar form we will be discussing. Don't worry. Don't be confused. I just want you to know the representation to understand which quadrant. And so this is the principal argument for first. This is not the principal argument. I'm sorry. If it was in the third quadrant, rather than moving in anti-clockwise direction, you can just move in the clockwise direction. That's the mean. Okay. We'll move. Yeah. Now, principal argument, as I said, it lies in the range of minus pi to pi, right? In the first two quadrant, it lies in the pi region, 0 to pi region. And in the second two cases, it came from minus pi. So the range lies between minus pi to pi. And this is what I have discussed. In the first quadrant, theta. Second quadrant, pi minus theta. Third quadrant, this is actually pi plus theta. If you multiply the negative sign inside, it becomes minus pi plus theta. So this is actually minus pi plus theta. And the fourth quadrant remains minus theta. Hope this is clear for you. Let's move. Yeah. Some properties of argument. This is the topic of very important topic. It's simple to understand also. I need you to remember this thing one more time. I need this for the proof only. That is, a polar representation of a complex number is r into cos theta plus I sin theta. I said how it came, right? Let me discuss that with you in detail. I'll show it once more. How did that come? If my z was somewhere over here, this is my distance to the origin. Let me say it's some r distance, right? This is my imaginary distance. This is my real distance. Let me say this y and this is x. So the general representation is x plus iy. So this is angle theta, right? Argument. So what is sin theta? Sin theta is y by r. That implies y is equal to r sin theta. And if it was cos theta, I can say it is x by r, or x is equal to r cos theta. Now when I add both and represent there, x is equal to r cos theta and y is equal to r sin theta. Taking r outside, so z is equal to r into cos theta plus I sin theta. So this is what is called as the polar representation. R is the distance to the origin, cos theta is the first part, sin theta is the second part. So general representation is r into cos theta plus I sin theta. Now let us discuss this. Argument of z1, z2 is equal to argument of z1 plus argument of z2. Don't worry about this 2k pi. It's just, as I said, it repeats after every 2 pi. So k can take an integer value and it can repeat after every 2 pi. So don't look at that now. Just look at argument of z1, z2 is equal to argument of z1 plus argument of z2. Argument of z1 by z2 is equal to argument of z1 minus argument of z2. Let's prove that very quickly. So, or I'll just prove it by discussing one more concept. That will be very easy for you. If I discuss with the polar form, it will take too much time. I'll discuss it with one more concept. So let's move on. I'll come back to this. So this is the polar representation. If my z was somewhere over here, as I said, the distance to the origin is r, and my imaginary part and real part. So it takes r cos theta plus I sin theta. And if it was in, in the second quadrant, or if it was in the third quadrant, both will take minus. If it was in the fourth quadrant, then cos will be positive and sin will be negative. This is r cos theta plus I sin theta. And de Moivre's theorem we will discuss. Don't worry about that. Again, to the next topic only. Next topic is the most important topic. So to discuss this is called the polar form, and mode z and the theta is argument, and more precisely the principal argument of z. Leave it. We have discussed it. Let's move on. So the polar complex number. This is what we have discussed just now. Cos theta is equal to x by r, sin theta is equal to y by r, x is equal to r cos theta, y is equal to r sin theta, z is equal to x plus iy. Represent that with r cos theta plus I sin theta. Take r outside, then becomes r cos theta plus I sin theta, where r is mode z and theta is the argument. So we have discussed this. So let's have the next discussion on the Euler's form. Very important. So let's have a quick discussion and too much sweating. So Euler's form is the same thing, like as you represent the polar form, z is equal to r cos theta plus I sin theta. You can represent in some other field, like z is equal to r cos theta plus I sin theta can be also represented as z is equal to r into e raised to I theta. This is what is called as the Euler's form. E raised to I theta represent this particular thing. So if you see, e raised to I theta can be expanded as cos theta plus I sin theta. Is that okay? This can be represented as cos theta plus I sin theta. And r is again the mode z, and this particular theta is the argument of z. Trust me, this is a very good hack for solving the method of polar form. There is an NCERT question I have brought that. We'll solve it with the Euler's form in a simple way. So let's move on. So this z is equal to x plus iy is the Cartesian form, z is equal to r cos theta plus I sin theta is the polar form, and z is equal to r into e raised to I theta is the Euler's form. E raised to I theta means cos theta plus I sin theta, and if it was e raised to minus I theta, then becomes cos theta minus I sin theta. The argument is then minus theta, okay? And modulus of e raised to I theta is equal to 1 if cos theta, root of cos square theta plus sin square theta. This is simple now, right? So you understood this. E raised to I theta is the Euler's form, and it's a very good thing to remember to solve every problem that comes with the polar form. Let's move on. So I have got some example. So let's solve that too. It's already solved. I need not solve it. So first is I is equal to, what is this? Euler form of, I think some z is equal to e raised to I into pi by 2. So here it's actually 1 into e raised to I pi by 2. So z can be represented as, so r is equal to 1. First thing, e raised to I pi by 2 is equal to cos pi by 2 plus I into sin pi by 2. Right? So this is cos pi by 2 is 0. I sin pi by 2 is I into 1. So simply this z is equal to I. I think that's why I wrote I is equal to e raised to I pi by 2. So e raised to I pi by 2 is equal to I. For e raised to I pi by 2 is cos pi by 2 plus I sin pi by 2. That is 0 plus I into 1. R is equal to 1 and theta is equal to pi by 2. Similarly, when 2 into e raised to I theta is equal to r is equal to 2, right? Sorry, this is 0, not theta. When it is 0, e raised to I 0 is equal to cos 0 plus I into sin 0. This is simply 1. So you will have 1 into 1, that is 2. So 2 is equal to 2 into e raised to I 0. 1 plus root 3 I can be represented as 2 into e raised to I pi by 3. Let's discuss that. E raised to I pi by 3 is equal to cos pi by 3 plus I into sin pi by 3. What is cos 60? It's 1 by 2 plus I into sin 60 is root 3 by 2. So this becomes 1 plus I root 3 divided by 2 into 2. The 2 get cancels. So this is an example for Euler's form. Let's move on. So what is de Moivre's theorem? Again, this is very simple. So you have cos theta plus I sin theta whole raised to n can be represented as cos of n theta plus I into sin of n theta. It's very simple. This cos theta plus I sin theta can be represented as e raised to I theta, the whole raised to n. Right? This is the beauty of Euler's form. So e raised to I theta raised to n. So I can write this as e raised to I into n theta can be then represented as cos n theta plus I into sin n theta. So this is what is de Moivre's theorem. N get multiplied with the theta. So this is the example. You can go through the PDF. I'll be just giving the link in the description box. You can download it and go through this example also. I'll move on. So this is an NCERT question. See how easily can be solved by Euler's form. It takes a lot of hell of time by solving this by rationalization and making into the normal form. Nothing. This is cos pi by 3 plus I sin pi by 3 can be represented as e raised to I theta, and theta is pi by 3. So this is simply e raised to I pi by 3 divided by, this is pi by 6, and there is a minus. So cos theta minus I sin theta can be represented as e raised to minus I theta. So this is e raised to minus I pi by 6. So a raised to m by b raised, a raised to m by a raised to n is a raised to m minus n. So this is simply e raised to I pi by 3 minus of minus, that becomes plus pi by 6. Right? So this is 3 pi by 6, that is pi by 2. This becomes e raised to I pi by 2. And we just discussed what is e raised to I pi by 2. It is cos pi by 2 plus I sin pi by 2. Cos pi by 2 is 0. I sin pi by 2 is 1. So this is, the answer is I. Simple. Now how much time, you just try from your home, how much time will you take with the rationalization and do with the Euler's form also. Let's move on. So this is another question, and before the discussion of this question, I just left the properties of argument, right? We'll start with the Euler form. So let's move back. Yeah. Let's discuss this. Let Z1 be cos theta. Let Z1 be some e raised to I theta 1 and Z2 be some e raised to I theta 2. Okay. So what is Z1 into Z2? There is one R also. R1, R2. So R1 e raised to, we'll take R. R into e raised to I theta 1 plus, into R into e raised to I theta 2. Now, what is e raised to I theta 1 plus e raised to I theta 1 into e raised to I theta 2? This is some, let's say, R square into e raised to I theta 1 into e raised to I theta 2. A raised to m into a raised to n is a raised to m plus n. So this is R into, or R square into e raised to I into theta 1 plus theta 2. Right? So the individual argument was theta 1, theta 2, and when you take the product, argument of Z1, Z2, take the product of this, then argument, this is argument of Z1, this is argument of Z2, and this is the argument of Z1, Z2, that is theta 1 plus theta 2. That means it's simply argument of Z1 plus argument of Z2, argument of Z1 plus argument of Z2, right? So with the Euler form, you can solve that. Do you realize this is same as the logarithm property? Log A into B is log A plus log B. You solve with the Euler's form. Similarly, you can solve the division also. Divide both. Divide this two. R get cancels. E raised to I theta 1 by e raised to I theta 2. So it becomes e raised to I into theta 1 minus theta 2. So argument of Z1 minus argument of Z2. Again a logarithm property. Third one also a logarithm property. Log a raised to n is n log a. Argument of Z raised to n is n argument of Z. And the fourth property is argument of Z conjugate. So if it was cos theta plus I sin theta, what is the conjugate of that? If it was cos theta plus I sin theta, this is e raised to I theta, right? The conjugate of this is cos theta minus I sin theta. And the argument becomes minus theta, e raised to minus theta, I into minus theta, right? So solve it the Euler form. It's very simple now. So learn the Euler's form once more, go through the PDF and also go through my classes and you will understand that. Okay, let's move on. Yeah, this question. So the question says, Z is equal to root 3 by 2, I'll write here, root 3 by 2 plus I by 2 raised to 5 plus, it's root 3 by 2 minus I by 2 again raised to 5. If a something missing over here, and represent and denote and real and imaginary part. Okay, this is R of Z and I of Z represent the real and imaginary part of Z. Then which among this is true? Okay, so let's solve this first. Again, the Euler's form come into rule. Root 3 by 2 plus I by 2. Root 3 by 2 is, can I write as cos pi by 6? Cos 30? Right? And what is sin 30? It's 1 by 2. So I into sin pi by 6 whole raised to 5 plus root 3 by 2 minus I by 2. That's again cos pi by 6 minus I into sin pi by 6 raised to 5. Again Z can be rewritten as e raised to I into pi by 6 raised to 5 plus e raised to minus I into pi by 6 raised to 5. Right? So again Z is equal to e raised to I into 5 pi by 6. Actually we applied the De Moivre's theorem with the Euler's form. Okay? Or you can write it directly with the Euler's form also. 5 times 5 pi by 6. Here, from here only you can write it directly. By De Moivre's theorem, cos pi by 6 plus I pi by 6 sin pi by 6 is raised to 5 becomes cos 5 pi by 6 plus I into sin 5 pi by 6. So that's De Moivre's theorem. I am solving the Euler's form. That's all. So this becomes I into sin pi by 6 and plus e raised to I into minus 5 pi by 6. Expand this. Cos 5 pi by 6 plus I into sin 5 pi by 6 plus cos 5 pi by 6 minus I into sin 5 pi by 6. So the imaginary get cancels and your answer is the imaginary part of Z is equal to 0. Fine? Let's move. Yeah. Now the most important and the last topic of the day is cube root of unity. The very important and entrance favorite topic. Cube root of unity you must understand very much. So cube root of unity, I'll just quickly say that and we'll move to the problem. If I say that Z cube minus 1 is equal to 0, this is Z cube minus 1, Z cube is equal to 1 and Z is equal to cube root of 1. Z is a complex number. So the root of this equation is cube root of minus 1. But the roots are not over. This is an imaginary. So it can have a real root and as well as imaginary root. So I just expand this. Z cube minus 1 cube can be written as a cube minus b cube form. So it's actually z minus 1 into a minus b into root of, a minus b into a square plus ab plus b square. This is z square plus 1 plus z. That's equal to 0. So I have now root, positive real root, and as well as an imaginary root. So this becomes 1. So z is equal to 1 is 1 root. Now we will solve this. This is a simple quadratic equation. I'll just off this. Yeah. Z square plus z plus 1 is equal to 0. By quadratic equation, I can write that z is equal to minus 1 plus minus root of 1 minus 4 divided by 2. That is minus 1 plus minus root of minus 3 by 2. Or minus 1 plus minus I root 3 by 2. So the roots are minus 1 plus I root 3 by 2, comma, minus 1 minus I root 3 by 2. So these are the two roots of the equation, z square plus z plus 1, and z minus 1 is equal to 0, z is equal to 1. So three roots you have. Now people, this minus 1 plus I root 3, this thing is called as the omega, and minus 1 minus I root 3. If you just go home and square this term, and you will get this. So this is actually omega square. Very important, very important. So this is omega square. If you square that, you will get this. If you square this, you will get that. Okay? Just go home and write. This is omega square. Now we'll discuss some properties of complex, this cube root of unity. The first very important property is 1 plus omega square is equal to 0. Okay? And 1 plus omega square is equal to 0. Why? I have 1 here. When I add these two, minus 1 plus I root 3 by 2 plus minus 1 minus I root 3 by 2, the two get minus I root 3 and I root 3 get cancelled up. Minus 1 plus minus 1 is minus 2. Minus 2 by 2 is minus 1. Minus 1 plus 1 becomes 0. So this is a very important property. 1 plus omega square is equal to 0. A very important property. The second property is omega cube is equal to 1. Second important property is omega cube is equal to 1. Just multiply these two and you will get that. Go home and write. Now, next property is we have omega is equal to omega square, omega cube is equal to 1. Now what is omega raised to 4? Can I write this as omega cube into omega? Omega cube is 1. So this omega. What is omega raised to 5? Is it omega cube into omega square or simply omega square? So omega cube is 1. And omega raised to 6 becomes omega raised to 3 into omega raised to 3. That is again 1. So generalizing the property, omega raised to multiple of 3 becomes 1. Omega raised to multiple of 3 plus 1 becomes omega. And omega raised to multiple of 3 plus 2 becomes omega square. Okay, this is a very important property for solving the questions. So let me get back to the slides. So this is what have we discussed. I'll just start this up so that you can see it. So we just solve this, z minus 1 into z square plus z plus 1, because z is equal to 1, z is equal to minus 1 I root 3 by 2 and minus 1 minus I root 3 by 2. It's omega and omega square. Next slide. This is a property, omega cube equal to 1, 1 plus omega square is equal to 0. And again, omega raised to 3k plus 1 and omega raised to 3k plus 2. Omega raised to 3k is 1. I have discussed this generalization. Omega raised to 3n is 1. Omega raised to 3n plus 1 is omega. And omega raised to 3n plus 2 is omega square. So this is simply again omega 1 plus omega square only. So this property and this property is same only. Okay. I need you to learn is omega raised to 3n is equal to 1. Omega raised to 3n plus 1 is equal to omega, and omega raised to 3n plus 2 is equal to omega square. And the next property is z cube minus 1 can be written as z minus 1 into z minus omega into z minus omega square. If you multiply these two, you will get back what is z square plus 1 plus z. How? Z square, you have z minus z into omega square minus z into omega. I'll just expand that for you. Z square minus z omega, and this is plus omega cube. Omega cube is 1. Take minus z outside, becomes omega square plus omega. From here, what is omega square plus omega? It's simply minus 1. So you get back this z square plus 1 plus z. And so it can be written as z minus 1 into z minus omega into z minus omega square. So next slide, we have question. Next slide. Again, one more question. Next slide. Okay, so since we have lacking with time, I'll discuss these questions in the next session. So next session will be very important. I need all of you to attend that, because we will be discussing some very good advanced questions, and plus I'll be discussing some NCERT, 1 or 2 NCERT miscellany questions and some beautiful advanced entrance questions, and plus these 2 questions also I'll discuss in the next session. Okay, so hope to see you again. Please subscribe to our channel if you haven't subscribed, and press on the bell icon for the more notifications, because there is a lot more to come. Thank you very much.